So here we go. Um, you went through this pre-quiz last week. If you have notes on that, I'd pull that out. So by the end of this lesson, you'll be able to describe what a Coulomb is and use Coulomb's law to calculate the net electric force. So if you have notes from the pre-quiz, you might want to check that out. Or if you have like amazing memory, you can check your amazing memory. Okay. Tell your neighbor. Correct answer is dangerous dinosaurs. Okay. So in chemistry, we focused on individual atoms or molecules, and you would count how many extra electrons there were. In physics, we care more about macro-sized objects, which have like quadrillions of electrons and protons. And so to like go and try to figure out the charge on that by counting how many extra electrons there are in each atom, like one, two, that'd just be ridiculous. That'd be like measuring from here to California in inches. It's like, it's not going to be wrong. It's just going to be ridiculous. So we need a better unit rather than just counting. So we've come up with this unit called a Coulomb. You could kind of think of it like a dozen eggs. Okay. Like we don't say we have 48 eggs. We say I got 4 dozen eggs. So a Coulomb is kind of like a dozen. It's just a unit of how many extra electrons or extra protons there are. Good with that? Give that one a shot. Give you a hint. D is not the right answer. Have a conversation.
Why do you think it's
Okay. If I said how many dozen is 2 eggs, would it be like be less than a dozen, right? It'd be like a fraction of a dozen. Correct answer here is C. Okay? One Coulomb has this many extra electrons. Okay? 1 dozen has 12 eggs. So if I have 2 eggs, I have a fraction of a dozen. If I have 2 extra protons, I have a small fraction of a Coulomb. You okay with that? Be 2 protons, which have this charge. Okay? Good with that? What a Coulomb is? That's what we're going for. Just a collection. It's just like a really big egg carton. And I just have 2 of those eggs in that really big egg carton. It's a small fraction of that egg carton. Called a Coulomb. You all right with that? Okay. So got this Coke can. It's empty. And we got this navally charged rod. What happens inside the metal of the Coke can when I bring this near? Oh, stop doing that. Wait for it. What's going on inside the metal of the Coke can when I bring this navally charged rod near? Tell your neighbor. Okay. Inside the can of Coke, inside the metal, the electrons do what? Here's your natively charged rod. What do the electrons do? They polarize. They're like, ah, right? They run away, leaving the protons. So, why, if the electrons ran away, why did the can move towards the rod? Okay. What's going on between the protons and the natively charged rod? Attraction or repulsion? Attraction. What's going on between the electrons and the rod? Repulsion. Which do you think is stronger? The attraction or the repulsion? Attraction. Why is the attraction stronger? It's closer. has a smaller distance. Therefore, it has a stronger force. You okay with that? It's a stronger force of attraction than this does of repulsion because it's closer to it. That's why neutral objects are attracted to a charged object, because of that polarization in the distance. Okay? Give this one a shot. I can't help but think you're distracted. Tell your neighbor. Correct answer is D. Good. Dangerous dinosaurs. They're repelling. Okay? Correct answer is C. Oh, yeah, Newton's third law. Good hint. Very good with that. C. A reaction, there's an equal opposite reaction. Thumbs up when you have a guess. Have a conversation. Tell them why you think so. Correct answer is? Correct answer is D. Dangerous dinosaurs again. Okay. So let's say I put more positively charged on this thing. That's just going to make both of those experience a greater force of repulsion. Does that make sense? So when we do this, the formula, when we put in numbers, when we get a number, that's going to be the force acting on this one and the force acting on that one because of Newton's third law. Okay, it's the same idea here. Okay, good. Tell your neighbor what you think. Correct answer is you don't know. It could be the same. It might be different. These are different. They experience the same force in terms of like their size, their charge. It's it. Is everybody okay with that? Does that make sense that they could have different charges, experience the same force? Everybody all right with that? Okay. C. So here's in real life, you have at your fingertips a whole lot of information, a whole lot of facts about a lot of different things. Hey, Google, tell me about this. And it is a really important skill for you to be able to filter out what's important and what's not. Okay. So in this problem, I've given you a whole lot of information, more than you had ever cared to know about sphere A and sphere B. What I want to know is what information do we need to glean from this that would help us answer how to calculate the electric force between these two. And here's the equation in the middle. Everybody good? You're going to need to know this. That's Q1, Q2, and D. K is given. That's a constant. Good? Okay. So we're going to do a little example problem here. I do know what K is. All right. Okay, that's our equation. Notice how I'm going to use that. So I've got 8.99 times 10 to the ninth. That's K. Okay. Times. Actually, I'm going to do D first. So D is going to be 30 centimeters. I need to convert that to meters. Okay with that? So that's 0.3 meters. And you square that. Now, just like I needed to convert centimeters to meters, I needed to convert microcoulombs to coulombs for the same reason, okay? Micro means times 10 to the negative sixth. Okay? There's very few things in here I'm going to tell you to memorize. This is one of them. 3 times 10 to the negative sixth. And notice I'm going to drop the positive and negative sign. You guys good? Okay. Beating on my wall. So I drop the positive and negative sign on the charge when doing the math. Okay, it's just 3 times 10 to the negative 6. And then here, Q2 is 15 times 10 to the negative 6. Which one's Q1 and Q2 does not matter. Just so long as you have both of them in there. Okay. And when you calculate this out, make sure you square the radius. You get 4.495 as your answer. And what are the units on that? Good guess. Nope. What did we just calculate? Force. Force is measured in newtons. Good with that? Questions there? Popular error is forgetting to square the radius. Good? Oh, yeah. Thank you. Good call. Part B. So this is the magnitude. This is the number. I want to know the direction. So I'm asking for which way is the peanut being forced. Tell your neighbor what's going on between the peanut and the strip. Attraction or repulsion? Which way is the peanut being forced? To the right or to the left? It's attraction. So the peanut is experiencing a force to the left. So to the left. Okay. The strip, if we were asked for which way is the strip being forced, you would say 4.495 to the right. But I didn't. I just asked for the peanut. So make sure you know which one is being asked. Good? Okay. If you're given more than one object, then you need to take it in pairs. If you're given more than one object, you need to take it in pairs. Thumbs up when you have a guess. Have a conversation. John. So this equation. Yeah. Correct answer is? Good, A. What's going on between 1 and 2? Repulsion or attraction? Repulsion. Which way is 2 being repelled? To the right. What's going on between 2 and 3? Attraction. Which way is 2 being attracted? Also to the right. So the net force, you would add those two together, and that would be the net electric force. Good with that? Okay. Same scenario, but what's the net force on 3? Tell your neighbor. Okay. What do you say? Correct answer is B. Beautiful babies. All right. Between 2 and 3, what's going on? Traction or repulsion? Traction. Which way is 3 being attracted? Between 1 and 3, what's going on? Attraction or repulsion? Traction. Which way is 3 being attracted? Also to the left. Okay. Net force is to the left. What about 1? Hold your comments to yourself. Hold your comments to yourself in your brain without engaging your vocal cords or hand signals or anything that would influence others. Okay. Before I turn you loose, I want to tell you the misconception that I thought when I was in your shoes. I thought that the fact that 2 is there would affect 1 and 3. Kind of like running interference patterns, like, gotcha. Okay. Here's why this is foolish. Okay, the stapler has a certain amount of weight, has a certain amount of force of gravity. When I put that over here, and now the table is in between the earth and the stapler, did that affect how much this weighs? No. Okay, same thing here. The presence of this or not, that does not affect what's going on between 1 and 3. Does that make sense? Okay. Have a conversation. All right. What's going on between 1 and 2? Repulsion. They're being repelled. Which way is 1 being repelled? To the left. What's going on between 1 and 3? Attraction. Which way is 1 being attracted? to the right. How does the force of attraction compare in size and magnitude to the force of repulsion? Why is it less? It's further away. Ooh. Does that make sense? Okay, so the correct answer is to the left. Okay, now changing the scenario. Let's say you don't know the magnitudes of the charges. Have a conversation and tell them why. Correct answer is D, can't be determined. Is it possible that the charge on 3 is great enough to counteract the fact that it is further away? Yes. It's definitely in the realm of possibilities. Good with that? Okay. This is going to be the hardest problem on your homework tonight. Okay. Just calculating this out. So I want to know the net electric force on object C. So what we're going to do is we're going to take it in pairs. Okay. So we're going to find the electric force between A and C. So we got K, QA, charge on A, charge on C over the distance squared. So that's 8.99 times 10 to the 9th times 14 times 10 to the negative 6th coulombs, because microcoulombs. And C, 7 times 10 to the negative 6th coulombs. Again, I'm dropping the positive and negative sign. And all that is over 0.5 meters. Remember to square that. And when you put that in your calculator, you get 3.5. The units on that are going to be newtons. It's a force. Okay. What's going on between A and C? Attraction. Which way is C being attracted? C is going to be attracted to the left. Good? Okay. We're going to do the same thing for B and C. So charge on B times charge on C over the distance squared between those. You got 8.99 times 10 to the 9th times 14 times 10 to the negative 6th. Nope, just sorry. 4 times 10 to the negative 6th times 7 times 10 to the negative 6th all over 0.3. Square that, and that answer is 2.8 newtons. Tell your neighbor which way 2.8 is acting. Tell your neighbor how you'd find the net electric force. The fact that they're going in the opposite directions, not because one's attraction, one's repulsion, it's just because they're acting in opposite directions, you're going to subtract those two. Your net electric force is going to be 0.7 newtons to the left, because 3.5 was greater than 2.8. Good? Worksheet for tomorrow. That's all I got for today.